The elements which make life on Earth possible seem so ordinary that we take them for granted. But none of it would exist without the sun. Whether we can see it through the clouds or not, its warmth and light keeps us alive.
The Sun is in fact a very ordinary star. It's a medium-sized star which is 4.5 billion years old and which emits light by a process of nuclear fusion. So the Sun is a star and also a thermonuclear factory.
Le Soleil, c'est une étoile et une usine thermonucléaire.
The Sun is not just a boring yellow ball in the sky which doesn't change. Of course, it changes over periods of 10 or 12 years from being relatively benign to being quite active.
Richard Marsden is involved in most of the studies of the Sun carried out by the European Space Agency, ESA, and is involved in studying it from space. But even before the space age, the Sun was extensively studied. Above all, scientists were interested in the role played by sunspots, darker patches on the Sun, which have been documented since they were discovered in the 17th century.
Soon after Galileo observed the first sunspots on the Sun, it went into a less active phase that lasted 60 years. No sunspots for 60 years. It was completely unusual and it corresponded with what we call a little ice age. The temperature of the Earth lowered by several degrees. We don't completely understand how solar mechanisms could disrupt our climate today, which is why we have to study it and understand how this star works.
That's the purpose of SOHO, a joint ESA and NASA observatory launched in 1995. Initially intended to work for 2 years, it's still operational. The data collected by the 12 instruments on board this observatory is essential. SOHO is in orbit more than 1,800,000 kilometers from Earth.
SOHO is really the star observatory when we talk about solar physics. It's really given us a new picture again of the Sun, primarily because it's in a very special place. It can look at the Sun continuously without being interrupted by the Earth or the Moon. It's given us the first view of the inside of the Sun, because using some of the instruments we've been able to look at vibrations on the surface of the Sun. And by seeing how those waves, which cause the surface to move up and down, change and then reflect on the inside of the Sun, we can learn a lot about the path that those waves took through the Sun and to come back to the surface again.
The temperature of the Sun is 15 million degrees centigrade at its centre and 5,500 degrees centigrade at the surface.
The magnetic activity of the Sun shows up as sunspots. On the Sun, we can see dark patches which are in fact concentrations of solar magnetic fields. These concentrations happen on the Sun's surface and accelerate the particles that we call solar wind. All of a sudden, we have gusts of solar wind arriving on Earth and disrupting our own electromagnetic systems. If astronauts spend long enough in space without special protective clothing, they're bombarded with electromagnetic energy. The Apollo missions in the 60s and 70s were lucky. They walked on the Moon during a period when the Sun wasn't too active and when there wasn't much solar wind. So they escaped any big electromagnetic solar windstorms.
Traveling at 470 kilometers per second, solar wind can have very serious consequences.
We need to also understand how the Sun affects life on Earth, and in particular the satellites that are in orbit around the Earth. And Cluster, another ESA mission, has really made great progress in helping us to understand the effects of the Sun on our Earth space environment.
Cluster is an international ESA mission comprising 4 satellites in a triangular orbit around the Earth. Their mission is to study the interreaction of the solar wind with the magnetosphere, a sort of magnetic belt which surrounds our planet and protects it against solar wind.
The thing we don't understand about the Sun is how the dynamo which produces the solar magnetic field really functions. The Sun is like a sort of magnet with a North Pole and a South Pole. It will be very interesting in order to understand the magnetic field emission mechanism to observe the Sun from above. I mean to hover above the North Pole and the South Pole and to look inside of this axis.
ESA's solar orbiter will do this when it's launched in 2017. In order to exit the ecliptic orbit around the Sun's equatorial zone, it will have to use another planet as a sort of slingshot. A previous mission, Ulysses, did it by taking Jupiter as a pivot, but this satellite didn't have any optical instruments on board.
What we'd really like to do is to bring optical instruments into that kind of orbit. And so what we're going to do with Solar Orbiter is to not use Jupiter because it takes quite a long time, but to use Venus. And that will get us sufficiently far out of the ecliptic plane to really view the poles for the first time.
Scientists are fascinated by the Sun, not only because of its physical influence on our planet, but also because of the answers it could give us to questions which become increasingly vital as our populations and our energy needs grow.
If we can reproduce the Sun's thermonuclear reactions on Earth, it's basically the result of fusing hydrogen and helium atoms, we'd have an unlimited source of energy. The temperature at the center of the Sun is 15 million degrees. Reproducing that temperature is very difficult, but I think that the techniques we're developing give us a good chance of having an inexhaustible energy source in the centuries to come.
If money was never an object, and if we could do all the technology that would be needed, there is one mission that I think would be fascinating to do, which would be actually to send a spacecraft into the Sun, really get into the surface of the Sun and try and understand some of the detailed physics. But this is something which certainly won't happen in my lifetime and is technically very challenging. But for a scientist, that's really the ultimate goal.
The universe is in constant evolution. Nothing is fixed. Even stars are born and die. Our Sun and our solar system are no exception, although the Sun won't burn out for billions of years.